The first reaction we are doing is a ring-open epoxide reaction, where 2,2-dimethyloxy ring is opened by a strong mineral acid, the hydrobromic acid. HBr contributes to the acidic environment of this reaction. First, the oxygen of the epoxide species is protonated by HBr, making it into a good leaving group that is now very unstable because of its positive formal charge on the electronegative oxygen, and will later become the alcohol functional group. One of the lone pairs on the oxygen attack the partial positive hydrogen, and the HBr bond breaks to become the lone pair on the now negatively charged bromide. This proton transfer also makes bromide a good nucleophile that will open the epoxide ring. After the first step, there are now two potential seats where carbon is electron deficient for bromide nucleophile to do a backside attack. In the first pathway, bromide attacks at the more substituted partially positive carbon center. This intermediate shows that the CO bond is in the process of breaking, and the formal positive charge on the oxygen is distributed as partial positive charge between the carbon and the oxygen. In the second pathway, the exact intermediate is shown, except now bromide is attacking the net substituted carbon. Note that now the partial positive charge is on the net substituted carbon, which is less able to stabilize it with electron-donating groups like methyl, making the whole transition state more unstable and unfavorable. Thus, bromide will not attack at the net substituted carbon, and the reaction will proceed only via the first pathway, where the partial positive carbon being on the most substituted side makes the transition state more stable. The bonds have completely broken and formed. The single final product is 2-bromo-2-methylpropane-1-O, with the hydroxyl and bromide functional groups on neighboring carbon, an indication of epoxide ring opening reaction. This nucleophilic attack releases the three-member ring string. Note that the electrophilic substitution in the epoxide ring opening under the acidic condition is in between SN1 and SN2 mechanisms, since while the backside attack by bromide is a characteristic of SN2, attacking at the most substituted side is a characteristic of SN1. Also note that while there is a partial positive charge on the oxygen during the transition state, the oxygen is still more electronegative and pulls electron density away from carbon, as indicated by the polar arrow. All carbons in the reactant are sp3 hybridized, but lack free bond rotation due to ring strain. When one of the lone pairs in the oxygen form the OH bond, the geometry of oxygen went from band to trigonopyramidal. Since bromide attacks 180 degrees from the back of the alcohol leaving group, here is a depiction. One way to tell in experiment if the reactant has been successfully transferred into the product is with IR scanning. While the reactant only has peaks indicating CsP3H bond at around 3000 to 2050 reciprocal centimeters, the product has an additional peak at around 3600 to 3200 reciprocal centimeters, indicative of the OH bond frequency in alcohol functional group. All carbons in the final product are still sp3 hybridized, meaning free bond rotation of the linear molecule. There's no chiral center. The product is already neutral due to protonation happening before nucleophilic attack, which is the reverse of an epoxide ring opening under basic conditions.
Right now we were talking about hydroboration oxidation. In this we have a symmetrical alkene in which we start with. The carbons are sp2 hybridized and they are planar. We react our alkene with HBH2, which is boron. It is a reactive gas and usually exists as a dimer. We have the electron-rich pi bond attack the H of the borane. The H then breaks its bond to the borane, and we form this intermediate. The formal charge is present on the carbon as it's breaking the octet rule. It doesn't have a full octet.
A side note here, it is the empty p orbital in the carbocation that allows the lone pair on BH2- to attack.
We understand this is a concerted reaction, and it happens all in one step. We would like to show the intermediate. Do not get confused by the top or bottom attack. This is why we're drawing the actual intermediate right here, the planar version, to show you that their top or bottom is possible, because in this only sin addition is possible. Do not get confused with the top or bottom attack. The same plane as which H was added is the exact same plane as which BH2 minus is added, because it is a 4-atom transition state. We then will now talk about the oxidation step. Oxidation is not well known in our scope, and it's beyond our scope, but alkyl boranes react readily with water and it burns spontaneously, thus it is oxidized. The OH simply switches with the retention of configuration. The exact same plane as which BH2 was added is the exact same plane in which OH is added to. If it was wedged, the OH minus would be wedged too. I would also like to talk about regioselectivity in this reaction. Not this one specific because we have a symmetrical alkene, but boron will bond to Li substituted carbon, anti-Markovnikov, and this is due to electronics and sterics. Right now we're showing you the IR spectras of both. We have OH difference in the last, and we have a C double bond C in the other. I also talked about bond polarity in both cases of the reagents, the HBH2 minus and the OH. The electron density is pulled towards the H in BH2 minus, and the electron density is pulled towards the O in OH. This is pretty much it for this reaction. I would like to say we chose a symmetrical alkene, so yes, again, consider regioselective in an asymmetrical alkene. But yes, this is the reaction.